From regaining range of motion to bodies in motion, we take you to a lab unlike any other, where researchers are exploring the connections between our balance and our cognition, how one impacts the other. It's a lab where flamingos, ballet dancers, and insects have been studied, and where humans, for the good of science, get the rug pulled out from beneath them.
We're gonna have something like that.
When you're deeply curious about a lot of different things,
So then in order to get this, I went from an insect lab to a human biomechanics lab to a animal research and neuroscience lab. So you should have more.
the often linear world of science
I also went through a dinosaur stage during grad school. So
can be a challenge.
I think this is a problem that a lot of young scientists face because you have to study this very, very specific thing that's even more specific than you could imagine.
Neuromechanist Lena Ting has taken her love of evolutionary biology and engineering and computer programming and neurophysiology and robotics
This model here.
and has married them together, creating a body of research that is changing our understanding of balance and movement. From why flamingos stand on one leg, to how insects and ballet dancers move, to floors that challenge our ability to balance, to robot walkers that could one day help us cross the street. The Neuromechanics lab in the basement of Emory University Rehab Hospital is home to Ting and her team and a host of fellow researchers working to change the future of how we assess, treat, and prevent mobility disorders.
Our primary research focus is in how we maintain our balance. So basically stand up. It's not something that people really think about until they lose their ability to do so.
Katie, can you go pulse up and down on your balls of your feet one more time? Yeah, I'll adjust to make it comfortable.
So the way that we've been studying balance control is by putting people on a movable platform. So it's a big device in the floor, you stand on it, and we literally pull the rug out from under you. And while we're doing that, we have cameras around the room and dots all over people, just like in the movies. In addition, we measure electrical activity in the muscles. So we stick, it's just like having your EKG done, but it's on all of the muscles of your legs and other parts of your body. And more recently, we've been adding what we call EEG, which is now electrodes on your head to measure brain activity. Try to map how the signals are coming from the sensory information through different parts of the nervous system, the spinal cord, brainstem, the cortex, and then generating a motor response in the muscles that ultimately is useful for having you regain your balance once we push you. We collect a lot of data, right? So we have lots of channels of muscle activity, of biomechanical movements, of forces, and then we have to interpret it. So that's the hard part of the job. That's where the engineering comes in. That's where the math comes in trying to look at coordination across all of these modalities.
This platform can also illustrate the divide between young and old.
When we started measuring brain activity in young, healthy adults, sometimes not much happened, right? And that means they're highly automated, and this is not a challenging task for them.
Balance is automatic, like breathing, not something you think about until you begin to lose it, which is what happens to many of us as we get older, hence the phenomenon known as stops walking when talking.
Because older adults, when they start to lose this automatic ability to balance, then they have to dedicate their attentional resources. And so they can't walk and talk at the same time. And so you might notice this in some people. They'll walk, and if you go to walk and talk to them, they'll have to stop because they're paying attention to their balance. That's not how we normally do it, or young people normally do it. They walk and they text. They walk and they're actually what you're supposed to be doing, which is looking for traffic, navigating, all of those things. The balance part is what we call an automatic function in a healthy person, where, and you may know this, you don't think about balance. However, it's a super complex interaction of many parts of your brain, your nervous system, and your muscles and sensory system that is constantly shifting around without your awareness.
Ting's research can help scientists and clinicians better understand what's happening in the brain before that first fall. And that understanding could lead to ways to maintain and even improve brain health to prevent falls. The lab also features a balance beam that progressively narrows to test people's balance. Most people cannot walk the entire length of it, but ballet dancers could.
In contrast, the ballet dancers, they didn't have to change their movement patterns from walking over ground to walking on the beam. And the important thing about that is that it's one of the reasons that we think you can identify ballet dancers by the way that they walk, because in doing this highly skilled training, they're not just reshaping the motor patterns that they're using for dancing, those are actually building on their walking movement patterns and changing those. And so you can actually see that in everyday movements and not just when they're dancing. So we know that for people who are highly skilled musicians and dancers, they're able to do lots of their skills without activating as much of their brain. So that means that those patterns get learned at a deep level, we call subcortical level, where it becomes automated, which doesn't mean that it's like robotic. It means that they're able to call upon these skills without much mental effort. And that means that they can spend their mental effort on the choreography and their artistic expression and anything else that they need to be doing beyond just getting the movements out.
These skills can be used for rehabilitation. Biomedical research engineer Rish Rastogi and neuroscientist Madeline Hackney are also ballroom dancers. Hackney is a collaborator of Ting's and a former professional dancer.
All right, everyone, when you get a chance, grab a partner and start dancing.
Whose research has shown that teaching modified tango classes to people with Parkinson's disease improves their balance and helps them do other tasks while walking.
T-A-N-G-O.
Hackney's tango classes inspired Ting to figure out how to make assistive robots more intuitive to use.
One of the things we noticed is that this, what we call haptic interaction, or this physical interaction at the hands, was incredibly important in guiding people during dance and helping people with Parkinson's walk. And in fact, when I went, sometimes they have you close your eyes, and in fact, people's movements get even better.
The end result could be futuristic walkers, robots that provide the balance benefit that comes from human touch.
We want it to act like somebody holding your hand across the street, but we don't understand why holding somebody's hand improves their balance. So that's what now we're using the robot to study the human and what that physical interaction imparts to their ability to walk.
To visit Ting's lab and the labs of her neighbors is to take a step into the future of personalized medicine.
Yep, that's good.
Around the corner is collaborator and physical therapy researcher Trisha Kazar,
Can I do left leg?
who rehabilitates walking patterns in people who've had strokes.
So with the cameras as well as the treadmill, we're able to measure how someone's moving after a stroke, which angle is their ankle or knee, how much is the difference between their affected or unaffected leg, as well as how much they're pushing off or pushing down on the ground. So just as an example, if I was to slow down my right leg, which we're doing now, so as you can see, my right leg is now going half the speed of my left, and that causes this limp, right? And it kind of mimics, even though I don't have a stroke, what someone with stroke would experience. Using these data, what we're trying to do is capture each person's what we are calling gait signature. So the complex, different kinds of 26 different variables for each individual, how they're moving, what are the differences between their affected and their unaffected leg, so we can target their gait individually, develop treatments that can now tailor to their own walking pattern.
There we go.
A few doors down from Kazar is neuroscientist Michael Borich.
This is a manipulandum. It's a robot that allows us to very quantitatively measure movement as well as to apply forces to one's movement to understand how people control their movements.
Borich and Ting are collaborating on exciting research looking at brain activity that connects our thinking and moving and how one impacts the other.
We are requiring participants to move in a pattern. And this pattern in this particular case is either in numbers or alternating between numbers and letters. And when we have individuals do this, it's a measure of attention, but it's also a measure of your ability to shift and move and so it looks at how flexible one's thinking is. So if you have to move, say, from number 1 to letter A, that is more challenging for the brain than, say, going from number 1 to number 2.
People who were not good at this set shifting were not as good on the balance platform, and brain activity was affected by both. That brain activity showed that cognitive stiffness is related to motor stiffness.
Imagine if you could do this pen and paper test and it might say something about your predisposition for a later balance impairment. That would be really important.
It could be an opportunity to intervene or prevent something, and it shows that what you do for your body affects your brain and vice versa.
And so there's evidence too that like some cognitive training might improve your balance, some balance training might improve your cognition. And again, this is an idea of where we shouldn't be separating balance and cognition into as distinct bins as we are in science.
At the beginning of her career, Lena Ting wasn't sure she fit in as a scientist. 20 years and over 90 studies later, she is a trailblazer who has found her balance, linking many fields of science, seeking a deeper understanding of our ever-changing brain and body connection.